Hello and welcome back to another episode of Getting into Git Oxide. And welcome back, Sydney.
Hi, Sebastian.
And today we still don't get back to the FS stats program. We discussed that before. It's not that I'm a terrible dictator or something, but we realized that now is the opportunity to talk about something else. So let's do that, as we can always go back to the stats program and do that when there's nothing more interesting to talk about. So now you might ask,
What could be more exciting than the stats program?
that's right. And it's about hashes in Git. Like which hashing function is Git using, and do you know some history about that?
Actually, I don't know too much. I mean, I've seen it in the code and from the multipack session that I think it's using SHA-1, and that is like the historical one, I'm guessing.
Mm-hmm.
And then the upgraded version would be the Sha256.
Yeah, that's pretty much it. I mean, SHA-1, they use a hardened SHA-1. I don't know how the hardening works, to be honest, because how can you make a hash better without making it a different hash? I don't know. But the hardened SHA-1, I think they started using because they realized that it's possible to generate collisions, even though it's still kind of hard. And these collisions, they break this invariant that you can always validate that your repository was not tampered with. So they already prepare for a couple of years, actually. I think 4 years ago, they started preparing, or maybe 5, for introducing a new or different hash kind. Different kind of hash, which is SHA256, like you said. And that, as we know, in 10 years, it's probably going to be broken again. And then you need SHA-512 or foobar, whatever is the thing then. And yeah, you can imagine it's not easy to do in Git because there's so many different file formats that and lots of code that kind of assumes it's 2020 hard-coded everywhere. I mean, that's already fixed by now, and they're kind of close to being able to support the SHA-256 hash and also different hashes, as long as they differentiate the hash by the size or its length in bytes. So that's kind of the trick. They assume they will never use a new hash that has the same length as a previous hash.
So it has to be longer, has to grow. I guess that makes sense.
Yeah, I think it makes sense as well. It's kind of part of what hashes do. Having a hash of the same length that is just so much better and is not broken, I mean, that would be great. But I guess you can always make a hash so that it's kind of a bit shorter or a bit longer so that it still works with your assumption that it's not the same size as something you already know. And of course, Git Oxide knew that from the very beginning, which is why it kind of tried to prepare, but in many ways it also didn't know, or I didn't know really what it means to support a different hash type. But over time it became a bit more clear how that would work. So I'm kind of giving a little rundown on where it started and where we are at now, and why the hashes all of a sudden became important again to me, because it wasn't expected that this would happen, but yeah, it just so happened, and it's kind of nice work too. I like it because it feels like a spring cleaning somehow. So git hash, there's this git hash crate which has this object ID or these object ID types. So either it's a borrowed or an owned version of it. And you can imagine that they already know, I mean, this was from the very beginning, they know what kind of hash they are.
Mm-hmm.
And this system here with Rust enum, it's not even encoding the hash itself by its length. It's encoding it with an enum, which of course would not have that limitation. You could have any kind of hash here and it would work. Because you can have this and now they have the same length, right? In theory, Rust could, or this implementation could do it, but we don't do it. We don't assume that. This also means that once we add SHA-256, one would expect a bunch of matches to break because then you have to handle this case. Matches stop being exhaustive, right? And this is also the idea behind that. Then it's easy to find places where you have to do something about Sha256 so that it kind of naturally tells you where to look. So that's the easy thing, of course, to put another enum variant here. And I'm thinking, you know, there are probably more efficient ways of encoding this so that you don't have an enum which takes a byte or so, and then you have differently sized arrays. So this structure kind of gets bigger, even though it still has to support the maximum hash size every time. So even though I'm digressing now, I'm just saying, I think this doesn't have to be an enum, and maybe one day it won't be, and it just internally handles kind of, maybe it's something I should refactor soonish, huh? Anyway.
You mean kind of dynamically just looking at the size of the hash and then figuring out, not just knowing what it's working with?
Yeah, but then again, I think I have to undo what I thought there. You always have to remember kind of what kind of hash it is to know how many bytes to take off your storage. So I think, yeah, it will stay in enum. Anyway, okay, good we talked about it. The other one, the borrowed version, is a bit different because this one is literally just a slice of bytes, like here. And it's a slice of bytes that has a validated size. So this one here sees, I'm a hash of 20, I'm a byte slice of 20 bytes, so I'm in SHA-1. So this one already is length based. This is why that works. So two different types, two different ways of representing them. This is kind of the standard Git way of doing it because the length of the bytes error slice matters. And that's the status quo. So in theory, with this OID, you already can represent any kind of hash, and that's cool because it's literally an object ID and you don't care how long the hash is or what hash is behind that. It's just usable. So most of the code already is compatible to using any kind of hash that exists now or in future. So that's nice. But of course, with the multi-pack index and the work there, I did realize that, well, the multi-pack index, it does know its hash length because it's actually stored in the file format, and you will see that newer file formats of Git, like the commit graph chunk file format and the multi-pack index file format, they store the kind of hash they're using in the file, which makes sense because otherwise, how would you know which sizes to assume for certain lookups and so on? And how to write that, right? I mean, it makes sense. And this kind of triggered me to look into this a bit more again and ask myself, is the existing implementation really fit for parameterizing the hash or not? And the answer was not really. It started all out with the loose object store, which can actually write objects. Because it's really easy to write loose objects, and that's the kind of standard way of writing new objects to a Git database. First you write a loose object, and then later you pack a bunch of loose objects into a pack file. So I was seeing this, and previously it actually looked like this. You had a hash kind parameter here, and that would tell for each write which kind of object or which kind of hash to use. And you can imagine, like what does that mean if you have that kind of API? Like where each object can have a different hash in theory. What does that mean?
You mean that it could be mix and match kind of, or like it could change during?
Yeah, it's kind of making it obvious that this can change. It kind of invites you to change it. Oh, this one I use a different hash. And for the other one, and you know, there's one thing that Git really doesn't like. It's mixed hashes in a Git repository. So that's not working at all. There's one hash and it must stay. And I don't know if there's a way to convert one to another yet, but I think I'm going to write that just for good measure to prove that my implementation actually works. But it definitely should only have one kind. So this had to go. And with this going, it became clear. This is a loose object store, by the way. And now it became clear that these things they had, or the loose object store had to know the hash kind that it should assume. When reading, it's not so important. When finding objects, it can actually find objects of any kind, of any hash kind, because you pass it the hash to find, right? So where is it? So when we look at the find implementation, which is kind of interesting, it's a kind of a side effect of this. You pass this OID here to see if something is in the repository, for instance, in the store, and it could be a hash of any size here. So this is already, independent of the actual hash of the repository, and I think that's fair, because usually you get these hashes from somewhere, and you get them from a source that knows the hash size, I guess, and respects it. So I guess it's okay. Of course.
So I mean, basically, instead of kind of telling the API what to use, it just infers it from the first one it finds, and from there it then kind of just knows this is the hash kind that should be enforced for this repository, and then it just automatically does it instead of you having to tell it what kind to use.
Oh, that's an interesting approach, like inferring from the first one that you see. It doesn't do that. It doesn't do that. It's immutable. It can't change itself, so it can't just change the hash kind that it assumes. No, it assumes these things are as stupid as possible. You just configure them. Like, as you see here, it now knows its hash kind to use, but what I'm trying to say is not in every interaction that you have, it actually respects that. But of course, you could check that, right? You could say, okay, self hash kind should be ID as ref kind. So that should match. And maybe in future.
Yeah, maybe I was expecting something like that, because you're saying that a repository can only have one hash kind, but I mean the underlying code can deal with different ones. So maybe I'm not really understanding why they're enforcing one.
Yeah, I mean, this code can, but I think it's just in the nature of this abstracted object ID, which can be any kind of hash. So like having this assertion is probably a good thing to do or to put in there, just to be sure. Let's make it a debug assert. Why not? Because these should be debug assert equal, and now we are there. That should be it. Because yes, there should be no weird mixing going on. It's kind of a bug if you try to throw in IDs that are of the wrong size. All right, and the same thing we should probably do here. So ID, and you see I make a debug assertion here because I think it's more like a thing you see when testing, and in the real world you shouldn't be able to see that. Let's see if that assumption holds true. So for writing, this trait here changed to not know anything about, or to not be able to configure that anymore. Instead, you configure it once per store, and that's that. And this was kind of the beginning of this whole idea of, let's look into more places where one might assume the hash size. And another interesting one, actually, let's have a look at this because I found that interesting. Here, there's this function called hash path now. And previously, this was called SHA1 path. So there you see it kind of assumed it's SHA1. Let's see, can I see what changed there? And what changed today? So previously, it was already kind of, the idea was that, of course, this can only deal with SHA1 right now, so I kept it named like that. And it was using the kind enum to match on something so that this would blow up if there's a new kind of hash all of a sudden. So that was already kind of prepared. But I was thinking, why can't I parameterize it? Why can't I make it in a way so that the code doesn't have to know? And previously, I think I did it that way because I didn't know how Git itself does it. How does it represent hashes that are longer? Does it still use this kind of idea that it has one directory with 1 byte and then the rest goes into the file? Answer, yes. So I checked the code this time, I checked Git, and Git does it exactly like that. So it's just parameterized, and it says, okay, hex version of the hash of any kind. Just do it like before. It's the same kind of, except that now we oh, I actually see a bug there. Because I think this should really have must use, so that the compiler tells me that the return value should be used. Let's run the tests here. Let's see if that must use actually works. Oh yeah, cool. So that might be a nice trick here. Unused return value of hex to buff that must be used. Because this bug happened because hex to buff tells me how many bytes it actually wrote.
Yeah.
Because this hex buff here, it's a buffer suitable to hold the longest possible hash. So, and this one just gives a slice, and it writes only a certain amount of bytes into that slice. So you really want to keep track of the hex length so that you can then only
use that portion.
Use that portion, yes. And now it's parameterized. And now this bug shouldn't happen anymore. Because I was looking at this and thought, no, I don't need it. It's fine. But I was wrong. And right now it only works because there's only one hash. So it has magically the right size. And maybe also the function name is a bit misleading because it's telling you, oh, I give you a hex buff, but it should tell you, hey, it's the longest one. So this kind of implies that you probably have to deal with shorter hashes as well. And you see, this is done to avoid allocations. You want to have a buffer that is big enough to hold the worst possible hash or the longest possible hash, and then you might not write it all, so that this is all allocation free. And then you just write to it, and this one does the right thing. And maybe there's even a better way. Maybe you can even return just this portion of that buffer so that you can just use it. You know, what about, how would it be if it could just return the buffer, the slice it actually wrote? That would be nice. So then you wouldn't have the issue. Maybe like I have now. But I think I didn't try that. Oh. For a reason, because I was afraid of ownership. You know, like if you have something mutable going in, how can you return something immutable to it? Because that means there's aliasing going on. Now we have a reader and a writer to the same section, and that wouldn't work. So interestingly, there is this thing that I didn't dare to try using, which is buff split at mut. So look at this. Because it knows that it is non-overlapping because you give it a midpoint, it actually gives you mutable sides of the same thing. So this allows you to cut off a part that you're not interested in, and in theory, you know, reuse the other. But I don't know if that actually works. So let's make a little test here without breaking the world. Hex to buff new. So here we would then, and I still don't think it should work, because what about lifetimes here? Like how can it I could do this in theory. Okay. And then we have destination in the reminder. And then we split it at num bytes hex. Okay, now we can just write it into destination. Yeah. Must be mutable, I think. Oh yeah, split at mut, right. It should be mutable as we get it returned, and this doesn't have to be mutable. And now in theory, I mean, what I really want to return is this, destination, and I don't care about this reminder. And I don't know, does it work? No. Same. Declared with different lifetimes. So I can't return this because naturally this now changed lifetimes here.
Mm-hmm.
And this is done intentionally as well so that you can't just do exactly what I do here. Let's see how this works. How does this work? It's interesting. It doesn't even declare any lifetime. It knows it's still depending on itself. And then, yeah, lifetimes are never declared. And I think these are new lifetimes here. These are naturally new lifetimes that are not our own lifetime. And this means they can only exist, I guess, for the duration of the function that used that split at. So there's no information for Rust that would tell it that these live as long as buffer lives, you know, and this is why they are kind of temporaries. Yeah. Okay. Doesn't work like I thought. So this is the way. I think that's better. Okay. So it's good.
So the only other way would be passing a buffer in that is already the right size, right? That's I think how you could do it. And then maybe splitting up the function again. But yeah, if that's worth it, not sure.
That's true. But then the caller has to do more work, kind of. Has to get the size, and then I think that's a useful trade-off. And now we can't forget it. I use it in another spot. Let's see, I know that much. And there I use the hex lang correctly. No, yes, here. So when formatting for hexadecimal display, I rewrote this to be exactly the same. Oh. And there I kind of managed to do that correctly. And that works. Okay. Cool. So now this is generalized. And that led me to looking at the iteration of loose objects. Let's see. Because that was also interesting when I first saw it. I changed it already. So now when you create an iterator, you get the size of the hash in bytes. Because it has to know that what Git does there for its own iteration, it actually only looks at files that have the right length. And this is how it filters out files that don't have the correct assumed hash. And previously this code looked like this. And you see it was just hard-coded here. That's it. And now all you had to do is really generalize the decoding of the hexadecimal bytes, and this hex buff function is really useful. And there it uses the hash, the length already, so that's also good. There I also correctly did that, I guess. Okay. Now it's generalized, and that was all that was really needed to make iteration work, because this already is a filter. Previously it filtered hard-coded by Sha1. And I think what also was interesting is the implementation of this thing. Because literally it's an walk dir iterator, so an iterator that walks a directory that is configured to do the right thing. And I think it's also sorted, even though here that's not so obvious, but maybe it's not actually sorted here. Anyway, it's using a filter map. It's just calling, it's creating an iterator, and then it calls filter map on the iterator, which then gets a function, just a freestanding function, that is this loose store iter filter map. Somehow it's part of I made it part of the store here instead of part of the iterator, which is strange, because it definitely is more related to the iterator, which didn't have its own type. Because the iterator itself, this one, I can't show this now, unfortunately, that's just a type def. It's a type def that actually hard codes or knows this exact type here. And for that, we really want to look at the next change file to see how this type looked like. So this is a type def. And look what it does. I thought that was creative of me back then, because it spells out the actual type that you get when you apply a filter map to this dir entry iter. And I think the knowledge to take away is that the most difficult thing usually with these filters is to catch or to define the type of the function that you pass in. Because if this was a closure, you couldn't do it. Closures have this anonymous type, and you can't declare anonymous types here in the type def. You can't do it. So if you pass in a freestanding function, you can actually declare the type, which is literally this. And that's cool, because that allows you to know the type, because it's literally statically known and there's nothing owned there, because these are just functions that have no state. They're stateless, and this allows you to know the type. And that's cool. You can use that if you want to. So I wanted to, apparently. It's the only time ever I did that. Yeah. So as you can see...
How long did it take you to find out that type?
I guess I just copy-pasted the function here that I had.
Right.
And that's the type, literally. Right, see? You just take away the parameter names here.
Yes, right.
And it's literally that. So it's very syntactically clear why that works and why that is. I like it. It's not strange syntax. It's really the most obvious syntax you could imagine, I think. And that's the difference between, you can use that for closures as well, right? If you want to get a function and not a closure, if you want to limit it to freestanding stateless functions, you can by using this syntax. It's interesting because this naturally is an fn, like if you wanted to declare that, I can't write here, but this is an fn, right? Like if you wanted to make this generic, it's fn. It's not fn mut, it's not fn once, it's fn. Because it won't mutate itself and you can call it as often as you want.
Mm-hmm.
Makes sense. So this now had to become its own struct because we had needed state. So this requires statelessness. So I couldn't do what I wanted to do. I couldn't pass the hash length in hex. So now, I just deconstructed this, taking the iterator itself as inner value and then the actual length of the hash. And the implementation, I think, is kind of interesting because previously you could just do a filter map. But now you have to implement iterator for your struct and you have to implement filter map yourself. Like, how do you implement a filter map? I thought, wait, how does that work? And I thought, okay, well then iterate over the inner iterator. If it's something, great, then use your filter, and if that's also something, return it, and then you're done. Otherwise, keep doing this until you run out of items, right? And that's the manual implementation of filter mapping. I think that's what it has to be. I thought, can you do some fancy option or else and then, you know, have multiple options concatenated together there? But I think you can't, because then, yeah, it would break out too early or something. So you have to really consume the inner iterator step by step. But the function itself, the filter itself, could mostly stay what it is, even though also this is kind of like, this is a bit hacky. And I wanted to get rid of this null SHA-1 thing because it mentions SHA-1 anyway. So that's really hacky, by the way. And it's obvious when you see that there's a closure that is actually an f and mud that binds to something outside of it so that it can change a flag that then tells the outer calling function what to do. Like, this was really, it's because back then I really had to use the combinators here. I really had to do a map and map error, and this is what forced you to kind of do that. And now I just, you know, wrote more stupid code, let's say, that doesn't think it has to use these combinators all the time. And then, yeah, you just match on it. And if it's an error, you return the error. And if it's not an error, you return it here. And if you're still there, you know, this is much more straightforward.
Also works.
It works, yes. And it's more the way I thought you would write that. And that's the rewritten parametric version of that iterator. And now the loose object store is actually fully parametric, which led me to move on to the next thing, like, what do indices do? What do packs do? Because they don't have a notion of hash length or the hash kind in their in their file format, unfortunately. And then I ask myself, what would Git do? Because that's usually what matters. And yeah, what we're looking at here is open packed Git. So at some point, so this is how Git opens a pack file. And at some point it has to see like what its trailer is, like its final hash. It wants to check that the file has the correct size, more or less. And this is what happens here. And you see it parameterizes it by the hash algo raw size. So the raw size is just the size in bytes. And this tells me that the whole file format is basically depending on being configured. So you tell it which hash size to assume, and then wherever there is a SHA-1 or was a SHA-1, you now assume just a hash of a given size. Mm-hmm. And this is how they make backwards compatible this file format that isn't actually compatible, which also means that somebody at some point has to know what file format it's supposed to be, and that's a git config thing.
Okay.
So for these files, it's kind of, it feels a bit whimsy, it feels a bit flaky, that the file itself doesn't know what it is, and you have to configure it. So if you change this configuration, right, then it totally breaks down, because Git then does the wrong thing and can't read its files anymore, essentially, which probably is okay, because also it won't do anything wrong. But it's, yeah, I really didn't think it through yet what that would mean for transforming a Git repository from one hash kind to another. I think for now Git doesn't do that, and you just have to start with the new hash kind. But I think it's really interesting to write something that is able to do that transformation and just rehash all objects, and also rewrite packs and recreate pack indices and so on, because you can actually do it. It's no problem at all.
It shouldn't matter, and then it's not a matter of configuring it anymore. It can be or could be completely automatic.
Yes. I just wonder how Git would do that. You know, there's a reason. I think I read somewhere that Git does not currently consider transforming one to the other. And if you look at the code here, you also know why. Because this would mean that one program that uses this function, these functions that are here, needs to have 2 hash sizes available.
Oh, yeah, true.
And how do you do that without, like, at some point you can't, this is a global and it's C, right? So you can just change it. You can change the, like, once you start writing, you can change the hash size to something else. Okay. But, like, I don't know. Like, what do you do with the objects you read? Or do you just, in lockstep, okay, I want to read an object, change the hash size to what it should be, and then from what I'm reading, and then change it temporarily to something else. You have to now start messing with a global variable that really, you can probably do it. In a single thread, you can do it. Okay, you can. But, geez, it seems very... Whereas in GiG-09, it's not a problem because you have one source that is configured to read the right thing in what you know it's SHA-1, and then you configure a writer which gets the hash kind to write, and then it's probably done in a way, it's probably written in a way that it is able to determine, oh, my input hash ID is a different length, so I have to rehash the whole thing, which it can do because it can query the whole... It can query the object data, so no problem there. It's extra work because you have to decode the whole object once to get that hash, but it's okay. You can do it. And it's nothing that breaks you because it's just, something to configure. So this is why I'm looking forward to that, and then just see, okay, what would it mean to transform the whole Linux kernel repository into SHA256? How big would it be now? And how does Git itself deal with that and stuff like that? Would be, what does performance say? Like, I'm really interested in trying this because I know they can't do it. Like, if maybe I'm wrong, right? But as far as I know, they can't do it. And then it would be like, this is Hacker News. Here is a SHA256 version of the Linux kernel made by Rust.
Is the SHA256 already, let's say, fully implemented, up and running in Git? Like, is it already usable? Or is that something that's planned for the future?
Good question. I think it's usable to the point where you can read these repositories and maybe even write one from scratch, but I don't know if it's in the last detail already done. But it's pretty far because they started 4 years ago. I think one person was constantly going through the code base and changing everything. So I think it's pretty much there. They also have tests for that. It's probably worth trying.
So, but then I'm guessing at some point they must have a way to do exactly that, right? To convert from one hash type to another. Yeah. I think it'll come down the line, I'm sure. But GiG-09 can beat them.
I hope to be not only faster in this, but also, earlier, make it available earlier, but also be faster because GiG-09 will, of course, be heavily multi-threaded. And then you have your 15 gigabyte of throughput per second or 12 gigabyte throughput per second of decoding speed, right? Like, this is what I measured when verifying the Linux kernel pack. So you can do that too. And I think it's going to be super exciting when you then start writing packs at this speed, because honestly, this is like a copy at this speed, because like, see it like this. The packs themselves, they don't store the hash at all. So if you have a nicely packed Linux kernel, packed down to 1.3 gigabyte or something, 90 gigabyte become 1.3 gigabyte. That's a lot of work that some CPU has spent to get it that small. So you don't want to throw that away just because you change hashes, but the pack doesn't contain hashes. It just contains encoded byte streams, encoded entries. And what contains the hashes is the index file. And remember, when you clone a repository, what you get is just a pack. So the index is always generated then with the hash function that you specify. So this is how you can receive a SHA. You receive a pack. There's no SHA something pack. There's just a pack. And from there, you create the index of a hash that you want. And the same operation essentially happens when you would rewrite a peg to become a new peg, because you essentially just copy the peg and you decode it to write the new index. And that should be easy enough. Probably Git can do that. I would be surprised if it couldn't. But then again, this global thing, this global, you have to change it at some point. Otherwise, how do you write an index with the different hash? So yeah. But then Git Oxide would decode that with 15 gigabyte per second, or at least on some machines. If you have enough cores, it can do that. Which is basically your copy speed. I mean, it's like, you copy the file, you decode it. If you want, it's all the same. I don't know. It's probably something that can be so heavily optimized that you have, like your SSD, if it writes 8 gigabytes per second, you write 8 gigabytes per second for this thing. And half a second later, you get your index with the correct hash length. So yeah, that's going to be cool. It's going to be very fast for sure. So let's see if they can be that fast. I am curious. All right. Yeah. Hacker News. I want to go there once again. I want to get there once again. But yeah, this is how Git does it. And now, just as one example here, because I think I've done that already, let's show the file tree. No Git ODB we don't care about. We care about the initialization of the pack, data file init. And let's see, did I do that one already? No, I did not do that one already. So this one hard codes the hash size here. This is why I know it's not doing it correctly. I think I just overlooked something here. So it needs a proper review for sure. So see, this is kind of dangerous. And it also doesn't care about the trailer at all, which is maybe also something that should be improved at some point. So I think it does actually less than Git does, and usually Git Oxide shouldn't do that when it comes to checking sizes and so on. But no, wait, it can't really do that because it doesn't know that yet. Because past the header there's just a bunch of entries. Never mind, it's okay. I think I'm misunderstanding something here. The same wrong thought I had before when I looked at this before hand, and it's wrong. No, let's look at the index file because that's definitely doing it. So you see now when you create a new index at a path, you want to open it, you provided the hash kind that it's supposed to assume. And internally it just cares about the length of the hash, so just breaks that down right away. And then everything is parameterized by this. And that's already it. That's that easy. And when it's about accessing or verifying the hash, then you see it just uses this parameter instead of using a hard-coded length. And it's really that easy. So it's something that we can really do, and better do it now than later. And that should be fine that way. Yeah. And yeah, that's the kind of work. It's kind of really, it's super valuable to me somehow because it's relatively easy and straightforward to do. It doesn't require much, let's say, except for a keen eye. I do plan to look for certain functions in Git hash to validate that I don't misuse them like I just did, right? The shortest hash or the longest hash, then hard code that. But then once that is done, we are nearly at the point where we can actually add that new Sha256 variant. And implement a hasher that can hash or generate hashes of that kind. And then you can start testing and see if that actually works, or write that program that I was talking about that transfers one repository to another ID kind.
That'll be the final test.
That's the biggest one. That's a nice journey test for sure. And let Git also check it, GitFS check, just to verify that it really, really, really works. Have a second opinion, so to say. And Git is not really the second opinion, it's the main opinion. But it's, it's probably what I'm going to work for, transforming the Linux kernel pack or the Rust kernel pack. And having that and being the first, it's interesting. Let's see if I really am the first. This is relatively recent here, this clone. So is there some conversion? Oh, there is convert. What can convert do? Convert a file when checking it out and checking it in. Oh no, that's not it. Yeah. Hash info. Hash function transition. Yes. So this contains the plan on how to do it, and I think here is where, that's basically the rationale behind how they do it. And I think somewhere they say that they do not translation table. Oh, right. Oh, they even have a translation table from SHA-1 to Sha256. So that the old hashes stay compatible. Makes sense.
Oh.
Okay. Not to forget. Yeah, so they maintain backwards compatibility even if you have converted it. So maybe I'm wrong about the conversion.
I mean, I guess that makes sense, right? If you convert it, it should not be destructive to the entire history.
Yeah. The Linux kernel starts over. Forget all the hashes you ever knew. You just have something new now. And is there a non-goal? Transparently improving the security, intermixing objects. Okay, as I said. No protocol changes. Shallow clone script fetching some submodules. Okay. Allow complete transition away from SHA-1. Local metadata for SHA-1 can be removed from. Okay, so they start. I think this is it.
So I'm not really sure what that means, like adding support to the Git protocol. That means, like they said here, Sha256 repository can communicate with SHA-1. So how would that work then?
Yeah, it needs a translation table. Like if the server holds Sha256, but somebody local comes up with SHA-1, then you need to run.
There's a translation table in there. Yeah?
And maybe it's not part of the protocol. The protocol doesn't know about that. It just says, okay, here's what I can do. But it's interesting that it stays compatible. That's pretty cool. Requiring no action by any other party. That's interesting. So you can just do it on the fly somehow. You can communicate to SHA-1 server, so you really need this translation table. It also means you need 2 hashes, right? Like all of a sudden you need, like if you create a new object that's SHA256, you also have to hash it in SHA-1 to be able to update that translation table. And
so they're doing both in parallel all the time.
Yes. Users can use SHA-1 and Sha256 identifiers for objects interchangeably. Yes. Okay. Okay. New objects make use a better signature. Allow complete transition away. So this transition table then goes away. Creation of generalized repository conversion tool. Yeah, for service this is certainly interesting, but I really wonder how it can create that translation or maintain that translation table, because then you have another race condition there. Like if you add new packs to an object to an object database, in order to make this really valid for SHA-1 users, you need the translation table written. Probably you have to write that first, but then it's going to be a file that has a lot of hashes in it, like every hash twice. The SHA-1 and the Sha256, 20 bytes plus, I don't know, 30 bytes, 50 bytes per object at least. So that's going to be a bunch of bytes, and if you rewrite the whole file each time, that's going to be, that's going to be quite a write. So each time you add an object, in theory, you have to write that file. Sure, if you add multiple at once, then you can write that file only once, but it's kind of a worst case performance scenario. So I wonder how that translation table is going to look like, because I don't think they specify it here. Pack index. Oh, there's a new v3 format for pack index. So maybe this is also, I didn't know. And there you can probably have multiple hash versions or something. Okay. It's not using the chunk-based format, it seems, which is a bit sad. Okay, so there's a v3 format that I also can't read or write. And that's going to be the new one. The translation table, is that specified? Maybe not. Let's look for translation. No. So no file that is called like this. Transport helper, no. So maybe this is not yet implemented, maybe. But yeah, an interesting transition for sure. And GiG oxide has to be part of that. Oh my god. Yeah.
A lot of work up ahead.
Yeah. And now you have to read v3 of the index, and you have to do the translation table thing and maintain that as well, to deal with these in-between repositories. Yep. Okay. Fun. Yeah, but that's the kind of work. I hope to finish this tonight because it shouldn't be too hard, and then I continue with the multi-pack index implementation, the actual one that I was supposed to do today instead of what I'm actually doing.
Finished a little side quest today. Yeah.
Yes, side quest. Got off track there. But yeah, I hope that was informative.
And as always, yeah. Learned a lot about the entire Git ecosystem once again. Thank you very much.
And thank you for your patience, and I hope to see you another time when we maybe do some more on the stats program.
Looking forward to it.
And everybody have a nice day. Goodbye.
Bye-bye.